Okay, so I'm Madeleine Udell. I'm a PhD student at Stanford, working on convex optimization. And so I think the way that we became interested in Julia was that we started out in MATLAB, right? We've been somehow MATLAB people for a long time. Cleve Moeller, used to work on the same floor that my current lab is on. So somehow, with MATLAB sort of came out of this area, and we all liked it, and we all sort of bought into it in the early days, where I considered me broadly to be, me even before I was born. Okay. So people like this, right? It's very simple, easy linear algebra, and then you get a little bit stuck. So in particular, my lab developed a package called CVX that has about 10,000 users in MATLAB, and many people say that it's one of the main reasons that they're in MATLAB is because they have CVX, and it's a huge, complicated package, and no one really understands how it works except for one guy, and my advisor has been talking about, if this guy got run over by a truck, like, who knows what would happen, like, everything would be over because MATLAB's going to upgrade, and then, everything's going to break, and so it's terrible. Okay, so we knew we needed to get out. And so, right, okay, so if you need to get out of MATLAB, where's the place you should get to? Julia. So I started getting interested primarily when I started experimenting with some parallel matrix multiplication. And I realized that I could write parallel sparse matrix multiplication in straight Julia and get it as fast as MKL on 6 cores at least. So that was kind of shocking to me because it looked very pretty. So I thought, okay, so exactly. So I know at least 5 optimization algorithms that I can basically, as soon as I have parallel matrix multiplication, I can parallelize the optimization algorithm, and it's going to be great. So I'm very happy. But now what I need is I need to be able to write optimization problems in Julia. And so this is the way that I write optimization problems. So this is a way to make it easy to write optimization problems so you can feed them to solvers, and it's a different paradigm for doing that than what you saw before. It'll be interesting to see sort of how people think about these 2 different paradigms. Okay, so the first thing I should do is I should give credits. So I started out this convex modeling language package back in February, and then 3 undergraduates at Stanford got interested in it, which is actually a good sign. So we taught this class on optimization algorithms, and I put up as a possible project that people could help me on in CVX and Julia, and everyone was interested in it. So at least among the younger generation at Stanford, it seems to be catching on. Okay, so that's good. And I have to mention the people that made this possible to come up with the ideas both for CVX and in MATLAB. There's a CVX Pi project in Python that got started a year ago. We're already as fast as they are, and faster than the MATLAB version. And then 2 of the solvers that we've been most integrated with, ECOS and SCS, which are written in C. Okay, so first I need to tell you what is convex optimization. Okay, so it's been said that the great watershed in optimization is not between linear things and nonlinear things, although those words get thrown around frequently, but between convex things and non-convex things. Fundamentally, convex problems are easy, non-convex problems are usually hard. So what is the convex problem? Well, let's first talk about convex functions. A function is convex if it looks vaguely like that, it slopes up, it has a non-negative upward curvature. If you draw a chord of the graph, a line between 2 points that are on the graph of the function, should lie everywhere above the function. And what makes solving optimization problems where you're trying to minimize functions like that easy? Well, fundamentally, there are 2 really nice properties. One is that if the derivative is 0, you know you're actually at the solution. And the other is that if you're somewhere else, you can go down and you're going to get to the solution. There's no other minimum somewhere out to the side. So you can solve this pretty efficiently. Furthermore, if you know that you need this function to be below some level, if you're below some level when you're here and you're below some level when you're here, then anywhere in the middle, you'll also be below that level. Okay, so you're very happy if your function is convex. And it turns out that convex optimization is sort of a subroutine for most other kinds of optimization. We also need some other definitions. Function is concave if it's if you multiply it by -1, and that's convex. And if it's affine, if it's both convex and concave, so it's flat. Okay. So here's the traditional form of convex optimization problem. Usually people would write down they're going to minimize some convex function f0 so that some other convex functions are less than or equal to 0, and some affine functions are equal to 0. so you could like manipulate your problem to get into this form, maybe. You know, it might be a little bit gross. The other thing is that if you only know the functional form, there's actually not very much that the solver can do with that, right? The solver has to, you know, maybe what does it know about these functions? Does it know, it only knows how to calculate their values? Does it know how to calculate their derivatives? What are the properties of these functions? Does it know, you know, the more it knows about the functions, the faster it can solve your problem. So we like to think about convex optimization in a slightly different form, which looks like it's more constrained, but actually it turns out that I actually have trouble thinking of problems that don't fit into something like this form, that are convex. The form is this. I'm just going to minimize a linear function, subject to linear constraints, and my variable has to be in some cone. So what are things that are cones? One is just saying that my certain parts of my variable have to be positive. They have to lie in the non-negative orthant. Another kind of cone that I might be interested in would be a second order cone. So that says that my variables have to lie below some other value. The norm of the variables has to lie below some other value t. So if I have a program that only makes use of constraints that are in the positive orthant, then that's actually a linear program. So I could, you know, pass it, if I see that my problem is actually in that form, I can pass it to a linear programming solver. I can call anything in any of the optimization packages that are already integrated in Julia. You know, I'm very happy. But I don't want to sort of constrain myself that way. I could add in things that are in the second order cone. I could add in things that are in the SVP cone. But I want to sort of think of them all in the same framework, right? It's very simple if I can just say, look, my optimization problem is 3 parts. It has the objective, the linear constraints, and the cone. So just tell me what those 3 things are, and then I'm happy. Then I know what to do. But you might not actually want to think about your problem that way, right? Most people don't think about their problems that way. They think about their problems using functions. So we'd like to be able to get from a functional form to this form, because once we're in this form, like a solver would love this form, because they know everything there is to know about the problem, right? There's no question of like, you know, do I have first order or second order information? I actually know everything, right? Because these cones are very constrained. There's a very small number of them.
Could you say a tiny bit more about what you mean when you say cone?
So what do I mean when I say cone? When I say cone, so a cone, okay, I've got the definition of a cone up there, which is that you're in a cone if anytime you multiply yourself by a positive number, you're still in the cone. Okay, so things like the entire real line is a cone. Okay, the point 0 is a cone. The positive, the non-negative numbers are a cone. You take a non-negative number, multiply it by a non-negative number, you're still a non-negative number. And these other things are cones too.
And an ice cream cone, if it were infinite.
An infinite ice cream cone. Good, yeah. So the second order cone is sometimes called an ice cream cone.
Without ice cream.
Okay, but my goal with this package is to make it so you don't have to think about these things. So we'll think about them a little bit more later. Sure. Yeah.
Is this equivalent to requiring x to be all positive?
This is equivalent to requiring x to be all positive.
No, but can't you just do a linear transform of x that makes that the cone?
No, the ice cream cone. No, the ice cream cone is different.
Is different? Okay.
Yeah.
Semi-definite.
The semi-definite cone is definitely different.
So the entire real line is a cone, right? It has that property,
yeah.
right? So that would
right.
kind of the simple rule
and
is
the real line definitely doesn't fit in positive orthant.
If multiplying by positive scalars keeps you in the set, you're a cone.
Yeah, no, I got the rule, but I just wasn't sure if it was equivalent. So that makes sense to me.
Yeah. And so here we can say the set of matrices that are symmetric and have non-negative eigenvalues is also a cone, right? And this is actually a pretty crazy cone in certain ways. Okay, so that's the positive semi-definite cone. Okay, so why are we interested in convex optimization? Fundamentally, it's because we have fast algorithms for it, and they're provably fast. We can get the global solution. We know what the complexity of that's going to be, and then so we can use that as a subroutine in even non-convex problems. So that at least, you know, even though we can't solve the entire problem efficiently, at least we can solve the subparts efficiently. So it turns out this is used all over the place. Machine learning, statistics, control, finance. I mean, it's like, okay, it's everywhere. It's sort of underlying, a lot of numerical computation. Okay, so I want to tell you why you don't need to think about it that way. Okay, so we're going to use the package CVX on GitHub, and so what's the first thing that we want to do is we want to define our variables. Okay, so I can define a scalar variable, I can define a column vector variable, I can define a matrix variable. So here Z is a matrix variable that's 4 by 2. And here you can see that the representation is, here's the size of the variable, and any is the sign of the variable. Sometimes in order to infer convexity of the expression, we need to know what the sign of the variable is going to be. So you can also tell it that the variable is going to be positive or going to be negative. Sometimes you'll get an advantage doing that. Then you can operate on these variables to form convex expressions. And these are just, I mean, the expressions you form are just sort of normal Julia objects. The expression knows what its vexity is. So it knows if it's affine, convex, or concave. It also knows its sign. So here you can see, you can do, I mean, sort of arbitrary, you know, you can treat these variables as though they were just normal arrays, right? So you can index into them, you can multiply them by numbers, you can add them, and all of these things are just forming new convex expressions. You can also apply operators from a set of operators that know how to act on variables, right? So this looks like, you know, square root of x, right? It looks like the built-in Julia function, but we're actually using multiple dispatch. We've defined our own square root, so if it sees that you're calling square root on a variable, it knows, you know, I'm not going to evaluate this thing, right? I'm going to return a convex expression, which happens in this case to be concave, because square root is shaped like this, so it's not convex, it's concave. And it knows that if I take the square root of something, it's got to be positive. And also, I mean, it's going to implicitly constrain my variable x to be positive behind the scenes. So there are lots of these built-in atoms that we've already put in, and you can add and write your own. So you can take the positive part as the maximum, you can take the norm, we've got the 2 norm, the infinity norm, the 1 norm. So it's pretty flexible. You can make all these expressions. Now there's some things you can't do. So here we've tried to add the square of the first coordinate of y to the square root of x. And we're not allowed to do that in the context of this language. It says it's not DCP compliant. And that's because we're trying to add a convex thing to a concave thing. And so now if you add those two things together, it'll be convex in some places and concave in other places. We're not going to know the global convexity properties, so we're not going to be able to guarantee that we can solve that quickly. And this language does not allow you to write anything that you can't guarantee you're going to solve efficiently. So that's just not allowed. Okay, so we can also add constraints. We can, so you can add a linear constraint. Here we're multiplying the variable y by a matrix A and requiring that to be equal to b. And you can see that forms, okay, so what is that? It forms an expression. It's a 3 by 1 constraint, so this is actually 3 constraints in one, because we've got 1 constraint for every row of b. It's affine, it's an affine constraint. And it can have any sign. This is the expression on the left-hand side, and the expression on the right-hand side is just the vector b, and they have to be equal.
So you only have positive and negative, but you don't have non-negative and non-positive?
So, okay, so we treat positive and negative are in fact non-negative and non-positive. Oh. Okay, so
it really is math versus optimization world.
Yeah, I suppose, yeah. I mean, we could write, instead of writing pos, I guess we could write non-neg, but that just seems a little bit longer and more awkward.
Agreed.
And in fact, whether or not you get solutions that are sort of less than or equal to or less than is going to be something that depends on the solver that you're using, and in some sense, like, shouldn't be part of the modeling language. I mean, if it's part of the modeling language, it just constrains which solvers you use.
Maybe a more important question. Can you express that a positive definite matrix that if you type I, it'll be positive? Can you express that in your language?
I mean that
the I function on
yeah.
positive definite matrices is positive.
Yes.
Cool.
Yeah. So we have SOCPs in here so far. We don't have SVPs yet. We're hoping to have them by the end of the summer. At that point, like, that will definitely be true. That I's of positive semi-definite matrices will definitely be non-negative. Okay, so here we have another inequality constraint, and so we can have a convex expression be less than or equal to a constant, and that's okay because convex expressions that are less than or equal to something form convex sets. And so we're okay with that. Similarly, so you can put sort of arbitrarily complicated things in here, and it knows how to think about them. It's perfectly happy to let you have a concave expression be greater than or equal to something, and a convex expression be less than or equal to. Don't try to do it in the opposite order, because that's not convex, and it'll give you an error and be very unhappy. Okay, for example, right, so here I've tried to require that a convex thing be greater than or equal to something, and it's very unhappy. So it's basically telling you don't try to solve problems that I can't guarantee you a good solution. We'll talk more about how to infer that that's going to happen later. So right now this is just giving you a sense of how do you quickly model and solve problems. So it's very easy to build optimization problems in this framework, right? You can define your objective and you can write it down as a function, just like you would if you were writing down the math, right? You can define your constraint in the same way. You can say, please minimize this objective subject to that constraint. That's my problem. And it prints out a nice message telling you what your problem is about, telling you that it's not solved yet. Okay, so let's solve my problem. And here it's calling out to a C library that's doing the actual optimization. Right now it has ecos. We're working to integrate with other solvers. Okay, so now it tells you it's solved, it tells you what the optimal value is. You can query the optimal value. You can also just evaluate any of the expressions that depend on the variables. If any expression that depends on the variables, now it'll return to you what the value of that expression is with these values of the variables. You can get the value of the variable itself. And interestingly, you can get the dual value. So you can get the value of the dual optimization variables that correspond to each of the constraints. I'm not going to go into what that means too much. Happy to talk afterwards. Okay, so you can also solve maximization problems. You can maximize concave expressions. That's just equivalent to minimizing convex expressions. And you can also just ask to satisfy constraints. If you don't have an objective, you just want to find a feasible point. Satisfies all those constraints. Okay, so now I want to tell you more about this paradigm, about the kinds of operations that you're allowed to do and not allowed to do in order for us to be able to guarantee that your problem is still convex. This is sort of explaining the error messages that you saw before. And the basic idea is very simple. We're going to infer the convexity of expressions by induction. So we know that variables, we know their vexity, they're just affine, right? The variable is sort of affine in the variable, right? Okay, not even sure it makes sense, and we know their sign, because the user is allowed to define the sign of the variable when they put it in. Now we have a library of atoms that have known vexity and sign as a function of their arguments. So by composing these atoms with each other, we're able to infer the convexity of the derived expressions. And actually there's a cute website that was developed by another person in my lab that helps you sort of understand how these rules play with each other. But I'm just going to give a quick introduction. So as long as your objective is you're trying to minimize a convex expression or maximize a concave expression, and the constraints have convex expressions being less than or equal to something, concave ones being greater than or equal to, or affine being equal, then you're happy and you know it's a convex problem and you can proceed and send it to the solver and everything's going to be fine. Okay, so how do you infer convexity? And the answer is basically the chain rule. For non-differentiable functions, a little bit more complicated, but actually the rules are the same. If you compose two functions, they're convex. If one of them is convex and increasing, and the other one is convex. Okay, I'm not going to read through all of the rules. There are 4 rules. It's not very many. You can remember them using the chain rule. Basically, if you compose two functions, this one has to be convex, so that f double prime is convex. This thing is always positive. F has to be increasing, so that that's going to be positive. And then G has to be convex, so that that's going to be positive. And then the other ones are just multiplying that by minus signs. Okay, so simple example. Addition is convex and increasing in its arguments, right? In fact, it's affine in its arguments, and it's increasing because if the argument increases, then the result increases. Okay, so that means that if you add two convex expressions, it's still convex. Okay, that's a simple example, right? They get more complicated. So we have lots of atoms that we know how to do this procedure with. We've implemented, basically everything that you might want in terms of sort of array operations. So, normal arithmetic, indexing, transposes, dot products, reshaping, concatenation, taking the min or max. We also have a number of other functions that operate entry-wise on your matrices. So you can take things like sort of the positive part of the matrix. That's useful if you're trying to construct a H loss in machine learning. You take the square root, inverse positive. I mean, there's some things that, like, it's sort of surprising that they're convex, and that's why they need to be atoms, because you're not able to infer them automatically. Like the square root of x times y. Like, x times y is not convex in x and y. But interestingly, like, you know that the square root of x times y, you can actually prove that that's concave. So this is why you sort of need this library of atoms. So there's certain operations that you can't do just by sort of constructing the functions yourself by multiplying the variables and be sure that they're convex or concave. You have to define them as such, and you have to define a way to sort of translate them into a form the solver can understand. So the last atoms are ones that take vector matrix arguments and return scalar expressions. So here we have things like norm. We have the 1 norm, the 2 norm, the infinity norm. You can get the square 2 norm by using sum of squares. We have the vector norms of matrices, quadratic forms. Here's plot over ln is also an interesting one. Like, that doesn't look convex if you just look at it. It turns out it is. So. Anyway, so these are sort of fun things that you can play around with.
What is that? Plot over ln? What is that? Yeah, x transpose x.
X transpose x
Oh,
divided
now
by
I see.
y.
X slash. Okay.
Yeah.
I couldn't see from here. Now I see.
Oh yeah. X transpose x divided by y.
Got it.
Y is a scalar?
Y is a scalar. Yeah, and it has to be positive. Yeah. So some of these atoms, if you use them, they'll impose implicit constraints on what your variables can be. Like as in the case of whatever ln, y has to be positive.
So for the first two, p could be any number bigger than or equal to 1. But
We've only implemented 1, 2, and infinity because we're putting them in. Yeah, I mean, you have to be a little bit more clever if p is any other number in order to cast it as a conic program. That's definitely something that we look forward to including. So, okay, so what are some examples? You take the square of the positive part of x because that's convex and increasing. Actually, I'm not going to spend too much time on this because I want to get onto the examples. Okay, so interestingly, sometimes composing functions isn't going to work as well as using things that you know. So you know that the square root of the square of x is just the absolute value of x. And that's perfectly convex. If you try to put in the square root of the square of x, it's going to get very angry at you because it doesn't know. I mean, basically, you have to know that the convexity of one is exactly sort of the opposite of the concavity of the other, and that's something that's not encoded in the assumptions right now. Right, and as before, you can't add a convex and a concave function. Okay, so here's an example I wanted to talk about, which is global connectome modeling. This is a picture by my collaborator, Franco Castiglia at Stanford. And the idea is that you can take an MRI image of the brain, right? And you can figure out where, in every voxel of the brain, is there a lot of flow going in a certain direction or another direction. And you think that there's some white matter that's connecting different parts of the brain, and so electrical signals are traveling through this white matter. But if there's a fiber in a certain direction, there's also likely to be more water flow in that direction. So he's looking at very large images of the brain, figuring out sort of where there's flow, and then postulating where there could be fibers that are connecting very disparate parts of the brain. Then he's trying to, so somehow where they postulate fibers is this very local information. They don't use the global information. They want to then use the global information to figure out which of these possible fibers are actually real. So I'm going to use this as an example to show you sort of how you can use this library for fast modeling. So here's the model. We're basically saying that AX is like approximately equal to B, where B is the MR signal observed at every location in the brain. So every row of B is a different location in the brain. The columns of A are representing the possible fibers, and they're telling you how much flow you would expect at that voxel if that fiber were present in sort of a unit amount. And then the question is sort of how thick that fiber is. Is that fiber, actually not there, in which case the width is 0, or is it, somewhat thick and you're expecting a lot of flow to that fiber? So we're going to do some modeling. What are some things that we know about this model? Well, the widths should be non-negative because they represent like fibers, which are not there in negative amounts. And the errors we think are Gaussian because we know something about fMRI. So we're going to try to solve this model. How do we do it? Well, we say, give me a variable that's the size of my matrix, the second dimension of my matrix. I can write down my objective, the constraint, and then I can ask to solve that problem, and I look at the values, and I say, okay, well, those are nice values, but actually I'm kind of concerned because this one's really small and that one's really big. Do I really think that the widths of these fibers vary by that much? I don't know. Okay, so I'm concerned. I want to try changing my model and see how much the answer is depending on my modeling assumptions. Okay, and I'm also interested in like how much is the answer depending on the fact that I thought it was non-negative. So I'm looking at the dual vector corresponding to that non-negativity constraint and saying that actually only a small number of the dual values are non-zero. That means that only a small, like even though I'm seeing a lot of zeros here, so that means that somehow the true answer, like even if I didn't impose the constraint that the thing be non-negative, I would actually be getting a number of the entries to be non-negative. So that's actually kind of nice. Okay, so more modeling. I didn't like how much those widths varied, so I'm going to penalize widths that are really big. See how that works. And it turns out that when I do that, some of the widths go down, and the objective values are not too different. So that makes me happy. Even though, interestingly, the values that I get are very different, right? So it turns out that the solution I get is very different, even though the objective value is not very different. That means that the problem sort of has a pretty flat minimum. There are lots of sort of solutions that might be compatible with my problem. Okay, so I don't like that. I feel like I need to put in more a stronger prior, given that there's so many solutions that are compatible with the data that I've seen. My prior is that there actually shouldn't be very many of these fibers that exist. So I'm going to try to encourage sparsity, and the way that I'm going to do that is I'm going to add this lasso term in the objective to encourage sparsity. And I could add it in the objective, I could add it in the constraints. And the nice thing about this code is that it's very easy to do this, right? I can just add one norm term to my objective, solve it, I get something. And the model's more parsimonious. There are many more zeros in that vector than there were before. And once again, the objective value isn't going up by very much. So I like this model, now I'm done. Okay. So in the last 2 minutes, I guess, I have time to tell you how this actually works, which is actually pretty simple. We construct an abstract syntax tree that's describing the structure of each of the expressions in our problem. We can parse that into a canonical form because we know things about each of the atoms that we've used in order to construct this expression, and then we just pass it to a solvers. The construction of the abstract syntax tree is just done automatically while you're parsing for each objective and constraint in order to verify that it's really convex. Here's some representation of that. When you ask to minimize the norm of ax minus b, it says, okay, well first I'm going to multiply a and x, then I'm going to subtract ax and sorry, b, this is a typo. I should subtract ax and b, and then I should take the 2 norm of that. That's my objective. Okay, so it knows something about it. And this is actually quite nice because the abstract syntax tree doesn't depend on, it doesn't depend on the solver format. It also doesn't even depend on the convexity of the expressions. So if you have your own sort of fancy way of taking a convex program and turning it into a different form, if you don't want it to go to conic form, you can take this and sort of operate on it. Okay, but if I want to take this into a conic optimization form, here's the way that I do it. I introduce a new variable for each one of the atoms that I apply, right? So first I multiplied a by x, that's a new variable. Then I subtracted b from that, that's a new variable. Then I took the 2 norm of that, that's a new variable. And that thing is my objective, that's what I want to minimize. And I still have the same constraint that x be greater than or equal to 0. So what's nice about having only one variable per atom is that then each atom can sort of turn its it participates in one constraint, and it can turn its constraint into a conic constraint because it's going to know how to do that. The first thing we have to take care of, though, is that we've got this equality constraint between a convex function of its argument and an affine function, a constant. And we can't guarantee, that set is not convex. The set where a convex thing is equal to something, is not convex. So we relax that to a convex constraint. We just put in a greater than or equal to sign. And here's really where we're using convexity, because the problem is convex. We know that at the solution, this inequality is going to hold with equality. right? Because we're trying to minimize the v3, so we're going to want v3 to be as small as possible, so it's going to equal v2, right? So that's really where convexity comes in. And then finally, each of these atoms knows what its canonical form is. So it's going to take itself and say, okay, I know that I have to represent myself as an affine equality with all the variables on the left-hand side, so I'll do that. Here, once again, all the variables on the left-hand side, affine equality, I'll do that. Here, I know that that previous inequality means that this vector has to be in the second order cone, in the ice cream cone, and x has to be in the positive orthant. Okay, so in code, what does that look like? You take that expression, you call canonical form on it, and it tells you everything. You can see that this is actually like not very pleasant to look at. So the point is that you don't have to look at it and you don't have to construct it yourself, right? But actually, if you peer into it, you can actually tell that. So here you can see this is a conic constraint. So this is the one that's telling you that that the introduced variables, the second and third one, are actually in the second order cone. You can see that because these are both sort of -1s, so they're.
Is this giant negative number?
What was that? Oh, the giant negative number. That's the internal representation of the variable.
Oh wow.
So jump uses this cute thing where the variables actually have names. For us internally, the variables are they're just some unique ID, and so we're using Julia's built-in unique IDs. So you can see this one, the constant on this constraint is actually some vector. So that's the one that's making some affine thing equal to b. This one is the one that's multiplying by a, so you can see by the fact that there's this thing here that's probably a. Okay, but like you don't have to look at this. That's great. Okay, so you have to pass it to the solver, and basically, what does the solver take? It takes, linear function of the variables, subject to linear equality constraint on the variables, and the variables are in some cone. In this case, it's just the first one can be any real number. These two have to be in the second order cone, and that one has to be in the positive the positive orthant. And then, okay, so we can pass that to a solver. And actually, we're working with the Julia Opt team to make sure that you can pass things to conic solvers using a form that basically looks exactly like that. So you can specify what that vector is you're multiplying variables by, what this matrix is, what that vector is, and what these cones are, and you just pass it in that way. Hopefully you never have to think about that. But if you do, it won't be terrible. Okay, so now we're at conic forms. And we can pass it to the solver. Currently, as I said, we're calling a SOCP solver. We're going to have an STP solver integrated by the end of the summer. Okay, so last thing I mentioned is future work. We're integrating it back to Progbase so that we can call all the other LP solvers when we determine that the program that you're solving is actually a linear program. We're looking at larger backend solvers like SCS, which is the solver that came out of my lab that can easily handle hundreds of thousands, millions of variables. It's a first order solver for STP and exponential cones. That means, so once we have that new solver, it means we can handle atoms like log, exp. We can do things like logistic regression. Anyway, anything you want. So whatever your pull request is. If you'd like to contribute, we're very interested in new contributions. In particular, if they're atoms, if they're functions that you want to optimize that you can't write using these disciplined convex programming rules, you can write your own atom. The easiest way to do that is actually just write your function and have it call other functions, and that works just fine, of course. Otherwise, you do actually have to think about what these canonical constraints are. That's all. Questions?
Well,
Yeah.
thanks.
Yeah.
So you talk about parsing an AST, but my impression is that what you're doing is using dispatch to sort of.
So I'm using multiple dispatch to construct an AST. So I'm not using a macro to use Julia's AST. I'm making my own AST implicitly.
Right. So this is sort of like when you have like differentiation libraries or calculus libraries, and you declare a variable and then apply a bunch of functions to it. And
Right.
They build the AST
Right.
as the operation.
Right. Yeah. So there is some question about sometimes this is going to be slow. So if you're putting these things inside, huge loops, then probably it's not going to be the fastest, and you want to be using something that does the allocation on the fly in clever ways. So the saving grace here is that I guess we're really thinking about using this for things where you're composing more functions, you're making sort of many modeling decisions, but you're not sort of touching individual variables very often. You're mostly calling these sort of larger scale functions, like you're trying to compute the log determinant of the matrix or something. And in that case, the overhead isn't very large because the construction of the abstract syntax tree doesn't depend on the size of the variables that you're using. Yeah.
This is just out of curiosity, but I'm wondering if it would be possible to express the vexity rules as function signatures so that the vexity inference could actually
Yeah, so that's something we'd be super interested in. We've thought about doing that, and it seemed like it took about as much code to write sort of if statements inside these functions as it did to write sort of new sort of type signatures. Right, because you can use vexity as a part of the type. So it wasn't clear to us what advantage we would have by doing that. That would seem really cool. If you can tell us why it's going to be so much faster.
I'm not sure there would actually be any real advantage.
Okay. Yeah, so we wrote that at one point, and we were like, I'm not sure.
I think I'm more just sort of curious to see what would happen,
Sure.
how it would work, and what it would look like. I think
Sure.
I'm just curious.
Sure.
Yeah.
We can show you some test code that vaguely does that. Yeah.
To what extent can the solvers be written in Julia?
So it
Or
seems
should
like
be written?
so when I can already find a C solver for my exact class of problem, it's probably faster for me to link it in. When I'm just experimenting and trying to figure out what new solver I want to write, I'm going to do it in Julia.
You mentioned something being faster than the Python version. Is that the construction part?
That's the construction. That's the parsing part.
Okay.
And that's.
And then they're both calling the same C-lab version.
Yeah. The solving should be the same time. The parsing is faster here. Also, Python just crashes if you somehow have things that are too big inside it.
You also said something in Python was faster than something in MATLAB. I forgot what you said early in your talk. You said that some MATLAB library is also available in Python and it was faster.
I think it was the CBX. You were saying CBX.jl and CBXPy were both faster than the.
No. So I think CBXPy is slightly slower than the MATLAB version. They're basically competitive. The difference is that the MATLAB version has been developed, has been the full-time job of one guy for the last 10 years, and the CBX Julia version has been around for 3 months. So.
Is this somebody at the MathWorks too? The one guy?
No, he just thinks it's fun.
Where is he?
He's like a...
In a mountaintop somewhere in the middle of the...
Yeah, basically.
Okay.
Austin, Texas.
You may have addressed this, but so there are going to be certain, of course, things that algebraically can't be guaranteed to be convex, but an over-bounded domain might be. So that essentially the conjunction of the algebraic expression plus the domain makes it
Right,
convex.
exactly.
Is that
so
something
you'll see that in some of our atoms that require that there are
I see.
inverse
So
positive.
I see.
So if you write an atom that says, for example, we have inverse positive, right? The inverse of a number is not convex over its whole domain, but over positive x, inverse is actually convex.
I see.
So using that atom puts an implicit constraint on the x be convex. So you can write other atoms that do the same thing.
Okay.
Yeah.
So how hard would it be to return the sensitivity analysis of the device problem? Because it will really compute almost.
So once you have the dual values, the sensitivity analysis is very. Maybe you mean sensitivity analysis.
I guess in the sense of here's the solution and here's what I think the derivative is and on the spot. You usually get some sort of you get almost all the information from writing down the information needs to solve the constraints already.
Right.
So there's sensitivity with respect to constraints, but also there's sensitivity to how far downhill you are on the original objective function, right?
So you're saying, so you have the objective value where you are, and maybe the reason you're not at the global optimum is because of the constraints.
Yeah,
So,
something like
so
that.
the dual value of the constraints is going to tell you how much the constraints are pushing you, and sort of, I mean, that's the dual value of the
Right,
constraints is
right.
basically telling you that the gradient
Yeah,
of the
so-
objective
so-
is your
yeah, but-
point, but it's not telling you how far away the global optimum is. So for that, you probably want to delete the constraints that we solve.
Right, okay, so that
Yeah.
would be how you do it in this range.
Yeah.
Okay.
Yeah.
Well, my clock says 12:30, which
Great.
seems like a good time
Good
to
time
wrap,
for lunch.
so thank